Okay, greetings and good afternoon to everyone, especially for our lecturer, Prof. IR Dr. Muhammad Kir bin Muhammad Noor. My name is Fong Chun Leong. My matrix number is CD230275, and I'm about to presenting our group project. Our group project title is the analysis of buckling of a wind turbine. This group discusses code is BDA 21301 Solid Mechanics 2, and we are from section 4, group 8. Okay, for the next slide, I'm gonna introduce our group members. Our group leader is Muhammad Faris bin Marsin. His matrix number is CD23008778, and our second group members is Afiq Fahmi bin Armizan. His matrix number is CD23000008, and the third group members is Hilary Kim Jus. His matrix number is CD230115. Okay, and lastly is myself is Fong Chun Leong, and my matrix number is CD230275. Okay, greetings and good afternoon to Dr. Muhammad Kir bin Muhammad Noor. My name is Fong Chun Leong, and about to explain the first part of the video, which is the introduction. Okay, the buckling of a column is a phenomenon that occurs when a slender structural element, such as a column or a beam, fails under compressive loads. The element, like a steel or a concrete, are known for their strength. They are vulnerable to a buckling when subjected to excessive compressive loads or forces. Okay, second is a buckling. Buckling is characterized by a sudden lateral deflection or a bending of a column due to a loss of stability. This phenomenon is of utmost importance in structural engineering, as it can lead to a catastrophic failures if not properly addressed. Okay, the third is a wind turbine column. We have chosen wind turbine towers as our top analysis because it is one of the real world examples, and it is also essential for harnessing renewable energy, supporting turbines at a height that optimize wind capture. However, their slenderness and the exposure to the harsh environmental conditions make them vulnerable to buckling, particularly under combined axial compression and bending moments induced by a wind and dynamic forces. Okay, for the next slide, which is the continuation of the introduction, but we mainly focus of objectives. Our group project main objectives is to analyze the buckling of a wind turbine tower columns under compressive loads from external pressures such as wind, gravity, and dynamic forces. By using the Euler's buckling theory that we have learned in Solid Mechanics 2, Chapter 3, Buckling of a Column, we aim to evaluate the buckling behavior of wind turbine columns or identify the factors that influence buckling, and of course evaluation of buckling building load under assumptions that comply with the Euler buckling theory. Okay, for the second part of our group project, which is the literature review, we mainly focuses on theory and formulas that we use to solve a problem. There are three most commonly used formula to solve our problems in solid mechanics 3, chapter 3, buckling of column, which is the Euler's buckling formula, help us to figure out the maximum load a slender column can hold before it buckles. Okay, for the first formula, we use the critical buckling load. Critical buckling load is a maximum compressive load a structural member can support before it buckles. Below is the formula, which is PCR equal to pi square EI over KL square. PCR is the critical load and E represent the Young modulus. Meanwhile, the I represent the inertia of moment, K represent the uh, column end condition, and L represent the length of a column. Okay, on the right figure we can see is the column end condition. In each of the illustration in the figure above, different end of a condition of a column are demonstrated, showcasing their respective effective length factors, or K. The first scenario represents a column with a both end pins, which is leading to a K value of 1. Meanwhile, the next is the fixed free end, or the peak of a column with one fixed and other of a end free, resulting in a K value of 2. Okay, for the third figure showcase a column with both end fixed, resulting in a K of a value of 0. 0.5. Okay, lastly is the fourth illustration exhibits a column with a one fixed and the other end pin, yielding of a K value of 0. 0.7. Okay, for the next slide, which is the continuation of a literature review that we have learned, or the other formula that we use to solve the problem. The second formula is the yield stress. This formula determines whether the stress will cause a structure such as a side stand to a permanently bend or a yield before it buckles. Below is the formula, which is the sigma CR equal to PCR over A. Sigma CR represents to a yield stress or a load stress. Meanwhile, the PCR represent to the critical load, and the A represent to a cross-sectional area of a column. Okay, for the right side, we can see is the safety factor. After taking into consideration a safety margin, this formula determines the safe load, or P allow, that a column or structure can support without buckling. Below is the formula that we can use for a safety factor, which is the P allow equal to PCR over Fs. P allow represent to a allowable load that it can support without buckling. Meanwhile, the PCR represent to a critical load, and lastly, the Fs represent to a safety of a factor that we can use to also prevent the buckling from happening.
Assalamualaikum and good morning to Doctor. So, I will explain about the problem statement that included in our case study. We analyze about the wind turbines and why the wind turbines collapse, and what is the factor or the critical parameter that make the wind turbine buckle, as we can see in the photo below diagram. There is a photo of wind turbines in Lithuania farms in 215. where it is buckled, and you can see that the the column the column is bending over towards the gravity force. So the critical parameter is it is having too much axial load or forces, which is make the safety factor cannot be function efficiently, or maybe it is about the safety factor is not enough to contain the axial load. And since we know that wind turbines is exposed to the environment, so it is high chance for the wind turbine to having any unforeseen situation, such as when there is too much wind or too much load that comes from the natural environment. That is when the wind turbines cannot contain, and the safety factor is cannot contain the load that being act on.
For this part of presentation, I will be explaining the mathematical model that we have developed to analyze the buckling behavior of a wind turbine tower. Our goal was to estimate whether the structure is safe against buckling under the axial load applied by the weight of the rotors, the blade, and the nacelle at the top of the tower. As shown by the still images, we model the turbine tower as a vertical, center cylindrical column fixed at the base and free at the top, which is essentially a cantilever. We apply Euler buckling theory to predict the tower's stability when subjected to axial compressive force, ignoring the lateral wind effect for this simplified case. To make the model solvable, we apply several key assumptions. One of them is the column is a long, slender, and has a constant circular cross-section. The tower behaves as a cantilever, fixed at the base and free at the top. The material is assumed to be homogeneous, isotropic, and behave linearly elastic. And importantly, we assume that only axial loading is present and lateral forces like wind are ignored. For the governing equation, because we assume some of them, we apply the following formula. First, we calculate the cross-sectional area and the moment of inertia for the circular hollow column. Then, we determine the radius of gyration, which is used to compute the slenderness ratio. And if the slenderness ratio is high, which is usually around 120, Euler buckling theory becomes valid. Using that, we calculate the critical buckling load and stress and the corresponding buckling stress. Finally, we evaluate the factor of safety, which tell us how much stronger the structure is compared to the actual applied load. However, this model does have its limitation, which is it is assumed a simplified geometry. Real towers are often tapered, not uniform in cross-section. The boundary condition is idealized as perfectly fixed at the base, which may not be true in reality. Most importantly, we ignore lateral forces and bending moment caused by the wind, which are actually significant in real wind turbine operation. So, while this model gives us a conservative estimate of buckling capacity, a more complete analysis would include those additional effects. In short, this mathematical model gives us useful foundation for understanding the risk of buckling and highlight how safety and stability are verified in wind turbine tower design. In Table 4.1, we selected parameters that reflect a realistic utility-scale wind turbine. The tower height is 100 meters, which is common for 2 to 3 megawatt onshore turbine. and we assume an outer diameter of 4 meters and an inner diameter of 3.9 meters, representing a hollow steel cylindrical column, which is typical for modern turbine towers. For young modulus and yield strength, we use standard properties as found in mild structural steel. The effective length factor was taken as 2 based on our assumption early on of an ideal cantilever. Now for table 5.1, which summarize our calculation result, we calculated a cross-sectional area of 0.62 meters square and moment of inertia of 1.21 meter to the power of 4. Using these values, we calculated the radius of gyration as approximately 1.397 meters. Although we assume the tower is long and slender early on, we still calculated the radius of gyration and the slenderness ratio to validate that assumption. The slenderness ratio came out to be 143.1, thus exceeding the usual threshold of 120. This justifies using Euler buckling theory. From the buckling equation, the critical buckling load was found to be 62.697 meganewton, and the corresponding Euler buckling stress is about 101.124 megapascal. This is well below the material yield strength, which indicates the tower would buckle elastically before yielding. Now, finally, we applied a desired factor of safety of 2.1. The maximum allowable compressive load became 25 meganewton. This ensures a safety design by accounting for uncertainties like loading variation, material imperfection, and installation tolerance. So, in summary, our parameter choices are based on a real-world design practices, and our result confirm that the structure is safely within the elastic buckling range. Next, we will look at the limitation of this model and how it can improve in the future analysis.
So after we do the mathematical modeling, we know that we use the equation PCR, and in that equation there is moment of inertia. So when we do the moment of inertia, we need to determine the cross-section axis that we want to use. Usually we use the weakest link or weakest axis of the column in order to satisfy both axes and to prevent both of them to buckle easily, because if we use the strong one then the weak one will easily buckle. So after we do that, we need to verify the limit for buckling stress. So this step is very crucial, because if the buckling stress is higher than the maximum allowable stress, then the material will pass through the proportional limit, as we can see in the stress strain curve or graph. To be frank, if it is exceeding the maximum value of allowable stress, then the material will lead to permanent deformation and increase the possibility and chance for the material to fail easily. That is why we need to determine and compare our sigma or buckling stress by using the equation buckling stress equal to PCR, or critical load over area of the column, and it is needed to do the safety factor, because we know that there is unforeseen situation that we cannot avoid, especially when things that is exposed to the environment.
As for the discussion, we can say that the key challenges is simplified assumption perfecting column under pre-axial load, which is during the wind turbine column buckling analysis. There are several challenges that we surface, which is the wind turbine structures are actually encounter complex loading circumstances, including torsion, literal and wind forces, and dynamic vibrations. These factors, which could significantly affect the critical buckling load, we are not fully taken into consideration by the Euler buckling theory, as states it is ignored factors cross-sectional variation, residual stress, material and imperfections. As for the limitation of theoretical model, the changes in the cross-section shape, resident manufactural, stress, and material fault can all have an effect on a wind turbine. Column actual performance, our theoretical model either neglected or oversimplified. The uncertainty caused by the real world irregularities, which neglects bending moments, fatigue, corrosion, and long-term material degradation. As for the suggested improvement, we can say that to improve the analysis are more techniques such as finite element analysis, or we can say it as FEA. It could be employed. FEA can simulate various loading circumstances, nonlinear behavior, and structural defects. That furthermore experimental validation using scaled down physical model or data from actual wind turbine will failure may yield more reliable insight and improve the accuracy of the future studies, which we can say that conduct experimental validation with physical models or real failure data. So, as the broad application of column buckling concept, we can say that it was relevant to structural design of towers, buildings, bridge, and offshore platforms. It could be also enhance safety, reliability, and performance, and prediction in engineering design. So, in a conclusion, I could say that in this group project, it has brought to light how crucial it is to comprehend and column buckling when it comes to wind turbine towers. And the importance of buckling analysis is Euler's buckling theory helped identify critical failure loads in a wind turbine columns. Despite Adelaide's assumption, the study highlighted the key structural stability concerns. So in the finding then demonstrate how crucial it is to account for buckling when constructing tall, thin structures. From the knowledge of solid mechanics too that we are learning currently, is not the only important academically, but also practically necessary for us to all of us to ensure that the effectiveness and safety of real-world engineering applications with profilization of wind turbine and other renewable energy infrastructure such as mechanical principle will continue to be crucial to engineering innovation and sustainability. So in a real world application it could be there was a buckling is a primary failure mode in a thin axial load structures, such as future design must consider dynamic forces, material flows, and imperfection boundary conditions. So in the outlook, we can use the integration of theory FEA tools and experimental validation is a crucial and solid mechanic knowledge also supports safer and a more sustainable renewable energy for us. So that's all from us. Thank you.